this video lecture, we will introduce the concept of impedance and discuss the extension of Ohm's law in the phasor domain. I have already anticipated that the analysis of circuits in the phasor domain makes it possible to transform the differential current-voltage relationship typical of capacitors and inductors in the time domain into an algebraic relationship. So let us now consider a circuit consisting of a signal source generating a sinusoidal signal, Vc of t, connected to a capacitor. Featuring a capacitance C. Suppose Vc of t is equal to A, the cosine of omega t plus phi. Of course, this voltage Vc is also the voltage across the capacitor C. The current IC flowing through the capacitor, according to the differential relationship between current and voltage in a capacitor, will be given by C times the time derivative of Vc, which is equal to, in this case, minus C omega A times the sine of omega t plus phi. According to well-known trigonometric identities, IC of t can be written as C omega A times the cosine of omega t plus phi plus pi by 2. In the phasor domain, the sinusoidal signal Vc of t is represented by the phasor Vc bar equal to A times e to the j the phase phi, while the current IC of t, also sinusoidal, is represented by the phasor IC bar equal to C omega A e to the j phi e to the j pi divided by 2. E to the j pi divided by 2 is simply j, the imaginary unit, so IC bar can be written as j omega c a times e to the j phi. But a e to the j phi is Vc bar, so eventually IC bar can be written as j omega c the voltage phasor Vc bar. So in the time domain, the current flowing through the capacitor is obtained by applying the time derivative operator multiplied by C to the voltage across the capacitor. In the phasor domain, the current flowing through a capacitor is obtained by multiplying the voltage across the capacitor by j omega c. So, as anticipated, the differential relationship in the time domain has been replaced by an algebraic one in the phasor domain. The current voltage relationship in the phasor domain can be rewritten as phasor Vc equal to 1 over j omega c, the current phasor IC, or Zc times the current phasor IC. In this form, the relationship bears some neat resemblance with Ohm's law for resistors, where the voltage is obtained as the current multiplied by the resistance. Here, the role of the resistance is played by Zc, which is equal to 1 over j omega c, or minus j over omega c. Zc is called the impedance of the capacitor C. What we have obtained can be seen as an extension of Ohm's law to capacitors in the Phasor domain. Note that the impedance Zc is a purely imaginary complex number. The unit of measurement of the impedance, like that of the resistance, is the ohm.
The result we got here, that the time derivative in the time domain becomes multiplication by j omega in the Phasor domain, should ring a bell for those who are familiar with Fourier transform.
Actually, the differentiation theorem for Fourier transform says that if g of omega is the Fourier transform of g of t, then the Fourier transform of the time derivative of g of t is equal to j omega times g of omega. This is evidence of a relationship between phasors and Fourier transforms, which will be made clearer later on in this series of video lectures. So, in the phasor domain, the current IC flowing through a capacitor with a voltage Vc across it is given by j omega c Vc bar. Now suppose Vc, the voltage phasor across the capacitor, is given by A times E j phi. Then the current phasor IC will be equal to j omega c A e to the j phi, which is equal to omega c A e to the j phi e to the j pi divided by 2. In the complex plane, the phasor Vc will be represented by a vector with the length a and the phase phi. The phasor Ic will instead be represented by a vector with the length omega c a and the phase phi plus pi divided by 2. In general, in a capacitor, the voltage phasor is always lagging behind the current phasor by a phase pi by 2. Or, changing the point of view, we can say that the current phasor leads the voltage phasor by the same phase. Let us now consider a current signal source generating a sinusoidal current I sub L of t connected to an inductor with inductance L. Suppose that IL of t is in the form B times the cosine of omega t plus the phase phi. It should be clear that this current IL is also the current flowing through the inductor L. The voltage VL across the inductor, according to the differential relationship between current and voltage in an inductor, will be given by VL of t equal to the inductance L times the time derivative of the current IL flowing through the inductor. This is equal to minus L omega B times the sine of omega t plus the phase phi. This expression, according to well-known trigonometric identities, can be written also as L omega B, the cosine of omega t plus phi plus pi by 2. In the phasor domain, the sinusoidal signal IL of t is represented by the phasor IL bar, which is equal to the amplitude B times e to the j phi. On the other hand, the sinusoidal voltage VL across the inductor will be represented in the phasor domain by VL bar, which is equal to the inductance L times omega times B times e to the j phi times e to the j pi by 2. E to the j pi by 2 is simply j, the imaginary unit, so VL bar can be written as j times omega L B e to the j phi. Now B e to the j phi is simply IL bar, so VL bar can be eventually written as j omega L times IL bar. So in the time domain, the voltage across the inductor, VL of t, is obtained by applying the time derivative operator multiplied by the inductance L to the current flowing through the inductor itself. In the phasor domain, the voltage across an inductor is obtained by multiplying the current flowing through the same inductor by j omega L. So, as we have already seen in the case of the capacitor, also in the case of the inductor, the differential relationship in the time domain has been replaced in the phasor domain by an algebraic one. We can write the current voltage relationship in the phasor domain as ZL times IL bar, where ZL equal to J omega L is the impedance associated with the inductor. In this form, as we saw for the capacitor, the relationship is very similar to what we already know as Ohm's law, with the voltage obtained by multiplying the current by the impedance ZL. So, again, the equation we have worked out can be seen as an extension of Ohm's law in the phasor domain. Note that, as in the case of the capacitor, also the impedance ZL is a purely imaginary complex number. The unit of measurement of ZL is the ohm, like that of the resistance. So, given an inductor with inductance L, the voltage across the inductor, VL bar, is given by J omega L, the current IL flowing through the same inductor. Now suppose that IL bar is given by the amplitude B times e to the j, the phase phi. Then the voltage phasor VL bar will be given by j omega L B times e to the j phi, or omega L B times e to the j phi times e to the j pi by 2, or eventually omega L B times e to the j phi plus pi by 2. In the complex plane, the phasor IL bar can be represented by a vector with length b and phase phi. The phasor VL will instead be represented by a vector with amplitude omega LB and phase phi plus pi by 2. In general, in an inductor, the current phasor lags behind the voltage phasor by a phase pi by 2. Or we can say that the voltage phasor leads the current phasor by the same phase. Let us consider now a current source IR of t generating a sinusoidal signal into a resistor with resistance R. Let's assume that the current IR of t is expressed as A, the cosine of omega t plus phi. Of course, this current is the same that flows through the resistor R. By Ohm's law, we know that the voltage VR across the resistor will be given by R times the current IR of t, or RA times the cosine of omega t plus phi. In the phasor domain, the sinusoidal current signal is represented by the phasor IR bar equal to A times e to the j, the phase phi. The voltage VR, also sinusoidal, is instead represented by the phasor RA times e to the j phi. But A e to the j phi is simply the current phasor IR. So the phasor VR can be written as R times the phasor IR. So note that the algebraic relationship given by Ohm's law in the time domain is preserved in the phasor domain. Therefore, Ohm's law also holds in the phasor domain. The relationship between the voltage and the current in a resistor in the phasor domain can be written as ZR times the current phasor IR, where ZR is the impedance of the resistor, simply equal to the resistance R. In the case of a resistor, the impedance is purely real. So in the phasor domain, the voltage across a resistor with resistance R is given by the resistance R times the current IR flowing through the resistor. As we said, this is exactly what we get in the time domain, as prescribed by Ohm's law. Therefore, if the current phasor is given by A times e to j times the phase phi, then the voltage across the resistor will be given by Ra times e to the j phi. Both the current and the voltage phasor can be represented in the complex plane. In particular, the current phasor will correspond to a vector with length a and phase phi. The voltage phasor will correspond instead to a vector with length Ra and phase phi as for the current phasor. In general, in a resistor, the current and the voltage phasors have the same phase. For this reason, the current and voltage phasors in resistors are said to be in phase. Now I would like to briefly summarize the results we got about the relationship between current and voltage in resistors, capacitors, and inductors, both in the time domain and in the phasor domain. In the case of the resistor, according to Ohm's law, the voltage V across the component is given by the resistance R times the current I flowing through the resistor. This relationship is preserved in the phasor domain, where the voltage phasor is equal to the resistance times the current phasor. For the capacitor, in the time domain, the current flowing through the component is equal to the capacitance C times the time derivative of the voltage across the capacitor. In the phasor domain, the differential relationship is transformed into an algebraic one where the current phasor I is equal to 1 over j omega c times the voltage phasor V, or equal to j times minus 1 over omega c, the voltage phasor. Finally, in the case of the inductor, the voltage across the component in the time domain is given by the inductance L times the time derivative of the current flowing through the component. In the Phasor domain, as in the case of the capacitor, this differential relationship is converted into an algebraic one where the voltage phasor V is equal to J omega L, the current phasor I. We have found that in the Phasor domain, the relationship between the voltage across a resistor, a capacitor, or an inductor and the current flowing through it can be expressed in a form which is very similar to Ohm's law for resistors, so much so that we have defined this result as an extension of Ohm's law to capacitors and inductors, valid at least, again, in the Phasor domain. The proportionality factor between the voltage across the component and the current flowing through it is what we have called the impedance associated with the component. So for a component with impedance Z, the voltage V is equal to Z times the current I. We have seen that in the case of the resistor, the impedance is a purely real complex number, while in the case of the capacitor and the inductor, the impedance is a purely imaginary complex number. In general, the impedance can be used in the Phasor domain to represent the properties of a more complicated network than a simple resistor, capacitor, or inductor. This network might well result from the connection, in various configurations, of several resistors, capacitors, and inductors. In this more general case, the impedance will be a complex number featuring a non-zero real part and a non-zero imaginary part. As a complex number, the impedance Z can be written in the rectangular or Cartesian form as R plus Jx, so as the sum of a real part plus J, an imaginary part. In the case of the impedance, the real part R is called resistance, while the imaginary part X is called reactance. In the case of the resistor, the impedance is said to be purely resistive because the imaginary part is zero. For capacitors and inductors, the impedance is said to be purely reactive because the real part in that case is zero. More in detail, in the case of a capacitor with capacitance C, the impedance ZC will be given by RC plus JXC. We know that RC is zero in the case of a capacitor, so this impedance is actually equal to just JXC, which is equal to, we already know, 1 over J omega C. From this equation, we get that the reactance for the capacitor is equal to minus 1 over omega C. So in the case of a capacitor, the reactance is negative. In the case of an inductor with inductance L, the impedance CL will be given by RL plus JXL, where RL is 0, so ZL is simply given by J, the reactance XL, which we know is equal to J omega L. From this equation, we get that the reactance for the inductor XL is equal to omega L, which is always positive.
As a complex number, the impedance Z can be represented in a polar form as a modulus times e to the j the phase of z. We already know how to find modulus and phase of a complex number when the real and the imaginary part of that number are given.
As we have already said, the impedance is measured in ohms.
The properties of a passive component, or more generally of a network of passive components in the Phasor domain, can be alternatively represented by means of the admittance. The admittance, which is typically indicated with the letter Y, is the reciprocal of the impedance. So Y is equal to 1 over the impedance Z. Therefore, the relationship between the current and the voltage in a passive component in the Phasor domain can be expressed as V equal to Z times I, or equal to 1 over Y, the admittance, times the current I. Or we can write the current I is equal to the admittance times the voltage V. The admittance is, of course, a complex number with a real part and an imaginary part. In particular, the admittance can be written as G, the real part of the admittance, plus J, B, the imaginary part of the admittance. G is called the conductance, while B is called the susceptance. We have represented here the admittance in its rectangular or Cartesian form. Of course, the admittance has a complex number, can be also represented in a polar form as a modulus times e to j, the phase of the admittance.
The admittance is measured in Siemens or ohm to the minus 1.
Given an impedance Z with its resistance and reactance, one can always calculate the conductance and susceptance of the corresponding admittance. In particular, we know that by definition, the conductance Y equal to G plus JB is also equal to 1 over the impedance, or 1 over R plus Jx. If we multiply both the numerator and the denominator by R minus Jx,
we get R minus Jx divided by R squared plus X squared, or R over R squared plus X squared minus Jx over R squared plus X squared. What we have written is an equation in the complex field which actually works as a pair of equations in the real field. In particular, if Z1 is equal to Z2 with Z1 and Z2 two complex numbers, then the real part of Z1 must be equal to the real part of Z2, and the imaginary part of Z1 must be equal to the imaginary part of Z2. In the case of the above equation, this means that the conductance G will be equal to R divided by R squared plus X squared, and the susceptance B will be equal to minus X divided by R squared plus X squared. In pretty much the same way, we can find that given an admittance with its conductance and susceptance, we can write the resistance of the corresponding impedance, R, as G divided by G squared plus B squared, and the reactance of the corresponding impedance as minus B divided by G squared plus B squared. The rules we have already worked out to reduce the complexity of networks of resistors connected in series and or in parallel also holds for impedances in the phasor domain. In particular, if we have two components in series, one with impedance Z1 and the other with impedance Z2, we can reduce them to a single component with impedance Zs equal to Z1 plus Z2. More in general, if we have n components in series, then the equivalent impedance will be given by the sum of the impedances of all the components. So Zs in this case will be given by the sum for I going from 1 to n of Zi. If instead we have two components in a parallel configuration, one with impedance Z1 and the other with impedance Z2, the two components can be replaced with an equivalent one with impedance Zp equal to 1 over 1 over Z1 plus 1 over Z2. We can, of course, extend this rule to the case of n components in parallel, in which case the equivalent impedance Zp will be given by 1 over the sum for I going from 1 to n of 1 over Zi.
Let us apply as an example the rule for equivalent impedances to capacitors. So let us consider two capacitors, one with capacitance C1, the other with capacitance C2 in series.
Let's find the equivalent capacitor with capacitance C sub EQ. We know that the impedance associated with the first capacitor is 1 over j omega C1, while the impedance associated with the second capacitor is 1 over j omega C2. According to the rules for equivalent impedances, the impedance associated with the equivalent capacitor will be equal to Z1 plus Z2, or 1 over j omega C1 plus 1 over j omega C2, which is equal to j omega C1 times C2 at the denominator, C1 plus C2 at the numerator. And this, by definition of impedance for a capacitor, must be equal to 1 over j omega Ceq. The last equation tells us that Ceq must be equal to C1 C2 divided by C1 plus C2. This is exactly the same result we got when discussing about the operation of the capacitor. Consider now the case of two capacitors in parallel, one with capacitance C1, the other with capacitance C2. Let's find the equivalent capacitor Ceq. Again, the impedance associated with the two capacitors in parallel will be Z1 equal to 1 over j omega C1 and Z2 equal to 1 over j omega C2. According to the rule for the parallel of impedances, the impedance of the equivalent capacitor ZQ will be equal to 1 over Z1 plus 1 over Z2, which is equal to 1 over j omega C1 plus j omega C2, which is equal to 1 over j omega C1 plus C2. This in turn must be equal to 1 over j omega Ceq. From this last equation, we get that the equivalent capacitance Ceq must be equal to the sum of the two capacitances C1 and C2. This again is exactly the same result we got when we discussed the operation of the capacitor in one of the previous video lectures. Find the rule for equivalent admittances given two or more components in a series or a parallel configuration.